All right, in lesson 8, that previous lesson, we talked about continuous graphs. And continuous graphs is basically, remember, it has no endpoints, it has no basically funky bits. It doesn't have any non-permissible values, no asymptotes. And basically what we can do with a continuous graph is never lift up our, that was a little bit crazy, but we can never have to lift up our pen. Piecewise functions are obviously going to be a little bit different. If you just even take a look at this bottom example here, you can see definitely if I were to draw that graph by hand, I would have to lift up my pencil. And that's important. That's just kind of like a very basic way of thinking what's the difference between continuous and piecewise. And saying some functions are defined by different rules in different parts of their domain. So if you guys take a look at this right here, you can see that there's not really going to be one graph that would give us that situation. Like there's not going to be one f of x is equal to blah, and you're going to come up with that graph. Piecewise functions is basically I've got maybe many different graphs with different domains that we stick all together and we draw on the same grid. Okay, so again, it might be different functions on the same grid. These are called piecewise functions. Because of the different rules, there is an opportunity for the function to be discontinuous, which is different than what we just talked about at certain points. All right, so number 12, if we kind of take a look at this example, it's saying use the graph of y equals f of x. So right now we're not really getting into what is the specific parts of this graph. We'll do that in the next example. But right now we're just going to kind of look at each little section and figure out what is going to be our limit. So if I take a look at the first one, I here, what is the limit of this function as x is approaching 1? Well, remember, we've done this a million times now. We take a look when x is equal to 1, and we follow our graph up, and we look to see kind of what our y value is. And approximately here, I know the graph's a little bit off, but we can just kind of assume that the limit is going to be equal to 2. The next one, I, it's saying, what is the limit as x is approaching 2? And don't forget what this little negative sign means. That means from the left. So if I look at 2 now, okay, so I'm basically looking at this whole line right here. If I'm looking from x from the left-hand side, you have to be aware that it's kind of coming from here, and that point is approaching about 5. 1, 2, 3, never mind, 4, let's say. My graph's a little bit off. So 1, 2, 3, 4. Sorry, that 5 should be up here. So it's kind of approaching 4. If I take a look at 2 from the right-hand side, you can see it's going down here, and that's about 1. Now, again, hopefully this is getting kind of old and easy for you guys. The last one here, what is our limit as x approaches 2? Well, from the left side it's 4, from the right side it's 1, so therefore it's not the same, and it does not exist. Okay. So a lot of times with a discontinuous graph, you're going to get limits that definitely do not exist. Now this is a question that's kind of similar to what you're going to be seeing. It's saying state 2 values of x. So again, I'm just going to kind of star that because you're going to see this again, of x for which the function is discontinuous. That means that it's not approaching the same number from both sides. So obviously here we've got, or discontinuous, I shouldn't say not approaching from the same side, but it could mean that there's a break in the graph. Basically I had to lift up my pencil is kind of the easiest way of thinking about that. Discontinuous, kind of common sense. So here, if I look at our graph a little bit nicer, state 2 values of x, where I'm going to have to lift up my pencil. Well, obviously here, right? So when x is equal to 2, there's a bit of a funky thing happening at x is equal to 2. And then after that, I don't have to lift my pencil up here, but I do have to jump right here because this doesn't exist. So obviously x is equal to 5, there's another little funky part that's going to happen, and this is going to be a break in the graph. So discontinuous, you can look at 2 ways, either lifting up your pencil or you can think a break in the graph. All right, if we look at the next example, this is what we were kind of talking about. This is a piecewise function. So notice that I don't just have a regular old f of x is equal to blah. I've got f of x is equal to this guy, and this guy. That's three kind of separate graphs with their own domain, so their own little section, and we're graphing them all together to make something cuckoo bananas that's going to look like this right here. Okay, so let's do that individually. Now, this always seems to be, every time I've taught this course, many students have difficulty with this. And the main reason is because you guys have been spoiled. You have a graphing calculator in front of you, and you have been tempted to just plug everything into that graphing calculator and let it graph everything for you. Well, you've decided to take calculus, and this is obviously a higher level of math. And so what the expectation is that you can graph this without the use of technology. Bum, bum, bum. So there's many ways of doing this. You can use a table of values. You can go back in time and think about, back in Math 10C, where you heard about mx plus b, remember that old guy? And that obviously is going to be like straight lines with a slope and a y-intercept. You can think about basic parabolas like x. So a lot of kind of things that you're going to need to consider when you're graphing these. The first one, let's just take one at a time and go nice and slow. I've got my 2x plus 4. So I'm going to take y equals 2x plus 4. And remember that I do have a domain, which is really, really, really important. And I'm going to mention how to deal with that in just a second. But first, what we want to do is figure out, what does this graph look like? Well, this is in the form mx plus b. So remember that this is my y-intercept. So right away on this graph, I would have a point of positive 4. And we know that it's a straight line graph because I've got 2x plus 4. It's a linear. And my slope is 2, which means I'm going up 2 and over 1. So remember slope, 2 over 1. Now, obviously, my graph, I don't want to go up 2 and over 1 because that's going to take me right off my graph. So maybe I can go down 2 and back 1. So down 2, back 1, so I know I'm going to have a point right about here. Down 2, back 1, I'm going to have another point right about here. Now, this is all good. And again, you could basically, draw these lines and connect them. Don't do this, by the way. Just wait. But the one thing that I said was really, really important is this guy right here. And that's my x is less than negative 1. That's my domain. And that we really, really have to pay attention to. So when x is equal to negative 1, you can see I've got a point right here. That means that everything to the right of that point does not exist. So I'm going to take my graph and I'm going to limit it a little bit. Now, those of you, and again, there's always some of you that I lose right at this stage because you're like, oh my gosh, I don't really even know how to graph this. If you forget this kind of stuff, obviously take your review back in your 10C. You can even look back at those podcasts as well. But you can always do a table of values. And this kind of gets us out of any jam when we are trying to figure out a graph. So I guess method number 2 of finding this graph would be just looking at different values of x, and then obviously it's a linear graph, so really all you need are 2 and then connect the points. So what am I talking about here? 2x plus 4. Now the most important point is obviously x equals negative 1 because that's kind of like a cutoff point. So when x is equal to negative 1, all you would also have to do is just maybe plug that into your equation. So 2 times negative 1 is negative 2, plus 4 would give me 2. And you can see that we've got that point already drawn. And then all you need to do is choose another point within that domain. So let's say x is equal to negative 2. And when you do that, 2 times negative 2 plus 4, you can see that that's going to obviously give us 0, which again, we've already got that point labeled. So again, method 1 would be just kind of like use previous knowledge. Method 2, use a table of values, okay, and just plot different points to solve for that graph. And just so you know, you guys are expected to do this. Now there is one thing on here that is a mistake on my graph so far. It's saying x is less than -1. So this point right here at -1 actually has to be an open circle because it's saying x is less than that -1, not equal to. Okay, so that's the first little part of our graph done. Second part, and I know I'm taking a long time, but once you guys get the hang of this, it will not take that long. The second one is x squared. Well, right away, let's stop and think, what do we know about x squared? We know that this is going to be a happy face. And we know that this is the basic parabola that actually goes through 0, 0, right? We know that it's going to kind of be point here, and then it's going to go up in a happy face kind of thing. But the most important part is, again, like I've been saying, our domain. And I'll even do this just in a different color here. So our domain is this guy right here. And we really want to figure out what's happening around those points. So remember what I was saying, just use kind of like a table of values, a substitution method. So the first thing we're going to do is plug in -1 into my x squared, which is going to give me 1. So automatically I've got a point, -1, +1. And it is equal to that point, so I can definitely have a closed circle there. So again, if I just go back over that really quickly, all I did is I took this guy and substituted it into my equation to figure out what a coordinate on my graph is going to be. Now the next point, what do you guys think we should use? The 2. Absolutely. So let's plug 2 into our equation. So I've got 2 squared is 4. So that automatically gives me a coordinate of 2, 4, which I know is going to be, according to this guy, an open circle. So 2, 4, 1, 2, 3, 4 is going to be an open circle right here. And remember, this is a parabola. We already knew that this is a point on my graph. So it's going to be this kind of a situation. Okay. Piecewise functions always look a little bit crazy. Now the last graph here, this third one, again, we want to substitute in our values. So I'll do this in the last color. We've got x is greater than 2. So let's plug that 2 into our equation. So I've got -2 + 6, which is just going to give me 4. And remember that this is going to be an open circle. Now that coordinate is going to be 2, 4, which, crazy enough, we already have an open circle there. So we can just kind of draw over it or do whatever. And then what is the rest of this graph going to look like? Because it's a continuous from then on, right? X is greater than 2. It's going to go on forever. So what we need to do is just even choose another point that's in that domain, substitute it, and see where that point is. And guys, what is this graph going to look like? Is it going to be a parabola? Is it going to be a straight line? Hopefully you're whispering in your head it's going to be a straight line because it's in the form mx + b. And because my slope is a negative, I know that it's going to be a downward graph. So let's choose another point that's greater than 2. Why don't we just choose 3? So now I've got -3 + 6. So that's obviously going to be equal to 3. So my coordinate there is going to be, 3, 3. So 3, 3. Going to be right about here. And we know that it's a straight line. So we're just going to continue on forever that way. And this is what my graph is going to look like. So it's a little bit crazy. We had to do a lot of work to figure it out. But remember, just substitution. If you ever get stuck, substitution is the best thing to do here. So now let's go ahead, once we've got a visual of what we're dealing with here, let's go ahead and answer the following questions. So it's saying the limit as x is approaching -1 from the right. So -1 from the right. Well, -1 is here. From the right, we're coming this way. And obviously we're approaching 1 there. If I'm approaching -1 from the left, coming in this way, and that is approaching the number 2. So what can I say about the limit as x is approaching -1? Well, that limit itself does not exist because those two values are not the same. Let's move on to the next one. X approaching 2 from the left. So positive 2 from the left would be this guy here, because again, here's 2. So that would be 4. X is approaching 2 from the right. Well, it's also 4. That point does not exist, but definitely the limit does because these two numbers are the same. So what is the limit as x is approaching 2? Obviously, it's going to be 4. All right, now there's one more example on doing this piecewise notation. And again, I always find that students have a little bit of trouble actually graphing this within the domain. So I really encourage you, pause this podcast, try this question, and then see if you get it right afterwards. Don't just copy it down. All right, so for the following function, determine the following limits. We've got x squared if, we'll just do this first one, x squared if x is less than 1. Now remember, we already know that this is going to be a happy-faced parabola. We also know that there is a cutoff point where x is less than 1. So let's plug this point in, which is an important point, into our expression. So basically I've got 1 squared is 1. So I know that my first coordinate that I can plot is 1, 1. Now remember it's less than, so I need to use an open circle at that point. And we already know, like we said, this is a happy-faced parabola. We know that it has to go through 0, 0 because it's a basic x squared. So that graph is going to look something like this. The next one, this guy here, x plus 1. So we know x plus 1, it's going to be a straight line that's going to be increasing, right? Because we've got a positive slope there. Now I've got two important points, and what I would probably do if I were you is just substitute those values in, and then just connect the dots. Nice and easy. So let's do 1 first. So I've got 1 plus 1 is 2. So that means my coordinate is going to be 1, 2. So I've got 1, 2, and now remember this is greater than or equal to, less than or equal to. So that means I've got a closed circle at 1, 2. Then I know it's a straight line going up, and the next point that we can plug in is the 3. So I've got 3 plus 1 is 4. So that's going to be 3, 4. So 3, 4 is going to be right about here. And remember, I'm drawing an open circle because it's less than. My graph is going to go like this. And then the last section, I've got this guy here, negative x plus 7. Again, it's going to be a straight line going down because I've got a negative slope. I know that x is greater than or equal to 3. So again, I would probably take that point, substitute it in. So I've got negative 3 plus 7, and that's going to be equal to 4. So my point there is 3, 4. It's going to be a closed circle. So you might be like, wait a minute, I already had a 3, 4, and there was an open circle there. So what does that mean we can do? Fill it in. Now we've actually do have a point there. And then x is greater than or equal to 3, so that means I can choose any value that's greater than 3 and plug it in, and then just connect those dots. So let's just choose 4, how about? So I'm going to plug in negative 4 plus 7, so that's going to give me 3. So my coordinate would be 4, 3. So 4 and then 3 is going to be somewhere right about here. And then we know it's a straight line, so we're good to go. We can just connect those dots and draw the rest of that graph. So hopefully you guys are able to come up with this kind of graph on your own. Again, you're not really going to see anything too crazy. It's just going to be parabolas and straight lines. We're not going to give you cubic or anything like that. So just practice if you're having a little bit of trouble. Remember, it's all about substitution. Now let's answer these questions. So saying the limit as x is approaching 1 from the right. Well, hopefully this is getting a little bit old. 1 from the right is going to be 2. 1 from the left, so I'm coming this way now, that's going to be 1. So obviously if those two things are not the same, and very visually we can look to see, well, yeah, the limit definitely does not exist. It's not the same number. And if we take a look at 3, so here's our 3, we've kind of got this closed circle there. That's why it's maybe a little bit more confusing. Obviously 3 from the right, I'm approaching 4. 3 from the left, I'm approaching 4, and therefore the limit must be equal to 4, which is good. It does actually exist. So guys, as always, take a look at the bottom, do that page 28 for homework, and see the help desk if you have any questions.